everyone to today's exciting workshop. Today we are in for a treat. We are live and streaming in all parts of the globe. So good morning, good afternoon, and good evening to everyone from wherever you are tuning in from. So thank you for joining today's workshop. If you are returning from last week's workshop, you are in for, as I mentioned, another treat. We have Carlos Afonso returning to host today's bootcamp bound workshop, A/B testing and multi-arm Bandit for data science. We certainly would like to keep this workshop as engaging as possible. So we certainly welcome all of your questions and your feedback. But we definitely want folks to start letting us know where you're dialing in from. So in the chat box, certainly feel free to let us know which city or even state you're tuning in from. And we'll allow folks to join in and get settled. Okay, I see a few cities trickling in. This is amazing. See New York, see New Jersey. Fantastic. I'll give it a few more moments before we begin talking about some of the housekeeping so that we keep this workshop as interesting and interactive so that you're able to benefit from it. So as I mentioned, today's workshop will certainly allow for folks to learn more about their skills within A/B testing and multi-arm Bandit for data science. So certainly allow for you to drop your notes in our chat. There will be opportunities for you to provide your feedback. So just be certain that when you are providing your responses or your questions, be sure to add your questions in the chat using the all panelists and attendees drop-down menu, as we will have a few of our data science instructors also joining in today's workshop to respond to your questions as Carlos is engaging in the workshop. We will also have our admissions team in the chat as well if you have any questions about the New York City Data Science Academy. So my name is Melissa Vilmane. I'm one of the admissions officers here at NYC Data Science Academy. And for those who want to learn a little bit more about who we are, just know that our data science bootcamp and courses are available both remote live as well as online. We are also the only bootcamp that teaches and trains our students in both using Python as well as R. We offer very hands-on and real-life work experience through 4 industry projects that our students are able to complete as they train with us. In addition to this very immersive course curriculum, we also offer job placement support, which includes connections to over 500 hiring partners. We also have our very solid alumni network. I'm sure many of our alumni are also joining this workshop tonight. For our 2,000 alumni, provide access to opportunities across the globe as well. Now, as of late, NYC Data Science Academy is rated as the best data science bootcamp for 5 years and running. And also for our online data science bootcamp, we are voted the best online bootcamp by switchup.org for the past 2 years running. And we are very proud of those accomplishments as well. So a little bit about our admissions process. We certainly welcome data enthusiasts such as yourselves. And our enrollment process is very simple. Simply submitting your application online allows you to get in contact with one of our admissions advisors, such as myself. You are then able to schedule an interview where we can further understand your background as well as your future goals within data science. Once you are able to then complete our technical assessment, we will then be able to provide you with an enrollment decision on being able to gain access and begin your candidacy and your enrollment with us. So we certainly welcome all those who have questions about our enrollment process or certainly want to be considered for our boot camp. Our admissions team, as I mentioned, will also be joining this workshop, and you can feel free to ask questions regarding that process in the chat, and we'll be happy to assist you. Now, we do have upcoming boot camps where we are still accepting applications. You will be happy to know that our application deadline has been extended for June 26th. So we are still able to meet with you, learn more about your background. Certainly, if you are wanting to transition your career into data science, we certainly would love to meet with you sooner rather than later. Our next upcoming remote live online bootcamp is scheduled to start this upcoming July 6th, along with our full-time online bootcamp, as well as our part-time online bootcamp. So without further delay, I welcome you to join us in welcoming Carlos Afonso for today's workshop for the A/B testing and multi-arm bandit for data science. Carlos, the workshop.
Great, thank you, Melissa. So let me start sharing my screen. Right, welcome everyone. I noticed some of you are asking on the chat where to get the notebook. I just shared again the link on the chat for everyone. That link lets you go to a Google Drive, a shared Google Drive, where you can download this notebook. And that link was also sent to you in the reminder emails if you have the email handy as well. So you can get the notebook if you would like to follow along. However, I do suggest that you pay attention. It's not just going to be about the notebook and the code itself. We're going to try to explain some important concepts, and it's important that you pay attention and follow along as I present here. So today we're going to be talking about A/B testing and multi-arm bandit for data science. My name is Carlos Afonso. I'm one of the instructors at New York City Data Science Academy. And let's start. So I'm actually going to even start with a new kernel so we can do everything from scratch. The main focus today is not on the code again, so you can get the notebook and follow along, but we're going to talk about some important concepts, and the main focus is for you to understand those concepts. These topics are very common and widely used in data science, but some of these concepts are particularly confusing, especially for beginners, and so we're going to try to explain those concepts today. So the objectives and the outline of today's workshop: introduce these important concepts for data science kind of from scratch. So I'm not assuming that you know statistical theory, that you know what's a distribution, and so on and so forth. We're going to try to introduce all of these important concepts from scratch. The only thing I'm expecting people to know is how to count and how to play the lottery, how to pull out balls from, say, a bag of many balls, and then you get like a lottery game. So the objectives and the outcomes. So we're going to start by learning what's an histogram, and the histogram is going to be an important tool for us to explain the other concepts, and you'll see why and how. Because it's so important to actually have a hands-on activity for you to actually manually compute an histogram and manually draw an histogram. You can also do it in code if you have Python running, but I suggest that everyone actually does it by hand. I'll let you know when we get there. Then the main part is going to be A/B testing. Okay. That's going to be the core of today. A/B testing as a classic statistical method. And through that introduction to A/B testing, we'll talk a little bit about important concepts in hypothesis testing, like the p-value. And hopefully we'll clarify what those concepts mean. At the end, we'll have just an overview about the multi-arm bandit algorithm, which is kind of a more modern generalization of the A/B testing. and it's actually uses a reinforcement learning approach. I'll explain that when we get there. So just a quick reminder about the questions. So we have a very large group here. Normally in our classes, we have small groups and a long time. So we normally have questions as we go along. I'll be able to answer your questions as you have them and as I explain. But here, it's not going to be possible to have everyone on the mic because we have so many people and have everyone asking questions at the same time. So what you can do is to ask questions on the chat, and that we have other instructors there that are going to try to answer your questions in the chat. I just suggest that you keep the questions on topic so that everyone follows along and people don't get distracted with other topics. And at the end, we're going to have also Q&A session. So at the end, we'll answer more questions as well. So as we go along, try to stay on topic. If you have questions, feel free to ask them on the chat. There will be instructions to try to answer your questions as we go along. And at the end, we also have a Q&A session. Okay. So let's start with the first topic, histogram. What's an histogram? Generally speaking, is a graphical tool that helps us describe and understand the data. So it's a tool for descriptive statistics. It's a way of providing a summary of the data, in particular of showing the distribution of values in the data. So normally you have a data which has a bunch of numbers, and if you want to kind of have a quick view of what's the bunch of numbers in that data, you can create this histogram that kind of plots the distribution of each of those values in that data set. And we're going to show you actually an example. It's always better to do an example and to have some hands-on experience to see those concepts in practice. For that example, we're going to be using Python, and that's why we're using here this Jupyter notebook. And I'll be explaining the Jupyter notebook and Python as we go along. Again, the main focus is going to be on the concepts of A/B testing and hypothesis testing, but as kind of a side bonus, you're going to be learning a little bit about Python as well. Okay. So we're going to use an example to introduce this histogram. I'm going to use an example of doing some dice experiments, rolling some dice. And how can we simulate that with code? We can use a function in Python, which is called the choice function in the random package. So I'll explain what's a package and what's a function, but so that you can see, I have here the numbers in the dice, the numbers 1, 2, 3, 4, 5, 6. And if I run this function, it makes a random selection of those numbers. So this is like rolling a dice, and every time I roll a dice, I get one of the numbers between 1 and 6, and it's a random choice. So every time I run, I get a different number. So we're going to be using this to simulate the rolling of a dice. Okay? And what are we using here? We are using the random library, which we actually imported at the beginning. So libraries are well-written and packaged code that someone already wrote for you, and as functions for you to use very easily. Like in this case, we can very easily use the choice function to create a random selection of a number. In this case, a number that represents the result of rolling a dice. Random is the package, choice is a function inside that package. A function is a specific program that has a well-defined goal. In this case, the choice function's goal is to make choose something from a list of objects. Choose one object from a list of objects. And in this case, we have a list of elements in Python, represented by the square brackets. We have a list of numbers, and the choice function is going to choose one of those numbers randomly. So that's the concept of function in library. And now we are also using this data type in Python, which is a list enclosed with the square brackets, a sequence of numbers. So we have this list, which represents the numbers in a dice. We pass that list as the input parameter to our choice function, which is part of the random package. And the choice function is going to select one of those numbers randomly. So every time I run this, I get a different number. Now that gets tricky for doing workshops and explanations, because if your outcome is always random, then you may get some surprises. So there's a way of, while still producing random numbers, keep the results reproducible. That way is to use the random.seed. So the .seed just fixes the initiation of the random numbers, so that every time I run the same code, I get the same random number. So it's still performing a random selection between those numbers, but now because I fixed the seed, I always get the same. But I can get more and more. In this case, I will be running that same function, choice, 4 times. As you can see, I get the different numbers every time. So in this case, I got 4, 4, but then I got the 1 and the 3. The point is that if I run this again, I get the same sequence of numbers. Okay? So just for practical purpose for the workshop, I'll be using random seed so that my results are reproducible. And what you see here is what you'll see in the notebook that you already got, and that the final notebook you'll get at the end. So you see exactly what we are seeing here today. Right, so that's rolling a dice. But now we want to roll a dice multiple times to create a data set. We're going to use a for loop. Again, a for loop is an important concept in coding, and a loop is something that we use to repeat an operation multiple times over and over. And I'm going to show you an example here, and we're going to use the for loop to roll a dice n times. And a question for you that you can answer the question on the chat. Suppose that I have this fair dice, so a dice that has the numbers 1 to 6, and I'm going to roll that dice 60 times. A question for you to answer on the chat is, if I'm going to roll a fair dice 60 times, how many times do you expect, say, the number 3 to show up? Feel free to show your answer on the chat. Okay. I'll get back to it in a moment. I'll get back to it at the end of this example. You can think about it, and you can provide your answer in the chat, and so everyone can see your answer, and we'll get the answer at the end. So here we are again setting the random seed so that this is random but reproducible, and it's going to be the number of times we're going to run the dice, and this dice underscore results is an empty list, which at the moment is empty because we didn't roll the dice yet, and every time I roll the dice, I'm going to insert the result of that dice roll in that list. So this print is just for convenience, printing this is what you see here, the headings that are going to say this is going to be the roll, and these are going to be the dice number for that roll. Now, we want to roll dice multiple times, so we're going to use the for construct in Python. It's the keyword for, spaced with a variable that is going to track each time we are looping through that for. The I is going to represent our iterations. Now we provide a list of items to iterate for. This range n creates a list of numbers that represent the iterations between 1 and 60. In reality, Python starts counting at 0, so that actually creates a list of numbers between 0 and 59. So, and every time we do one iteration, I'm going to compute call again the random choice function to select a number between 1 and 6 randomly, and I'm going to assign that to a results variable. And I'll print the result together with the number of the iteration. So first I print the number of the iteration and then the result. And at the very end, just before going to the next step, I will append the result to the dice results list. So the append method or function is to add a new element to a list. So this append method is adding the new result to our dice results list. When it runs the first time, it's going to add the first number, the second time, the second number, and so on and so forth. At the end, our dice results list is going to contain all the numbers, all the 60 numbers from simulating these dice roll 60 times. So let's run it. And I'm actually going to be printing every step. So for the first roll, we got the number 4. For the second, we got the number 4. For the third, we got number 1. For the fourth, we got number 3. For the fifth roll, we got number 5. For the sixth roll, number 4. For the seventh roll, number 4, and so on and so forth. And if we go all the way to the end, for the sixth roll, we got the number 6. And now remember that we captured all the results, all these numbers, all the dice numbers in the dice results, and we can actually print all of those results here. And now we have this list, which is the result of rolling a dice 60 times and recording the result for each time. So we could do this manually, right? We could be here rolling the dice, but it's just very convenient that you can have these random functions that let you simulate random processes like rolling a dice. Now, we have this data set, which is the result of rolling a dice 60 times and the recorded number of the dice number that we got at each of those times. So we have 60 numbers between 1 and 6, and they represent those results. How can we make sense of these data? In this case, just 60, could be even more, but I'm going to show you a general way of summarizing that data so that you can get an insight about the distribution of values in that data. The first approach is to just create like a table, create a tally of the number of times that each of those different numbers shows up. And that's what we're going to do right now. So these prints are just for convenience to create this table-like output. But what we're going to do is, again, we're going to do a loop. And each time we're going to iterate through one of the dice numbers. So the first time we're going to look at the number 1. The second time we're going to look at the number 2, then the 3, the 4, the 5, and the 6. And each time what we're going to do is look at this list, the list of results, and count how many times each of those numbers showed up. So the first time we're going to be looking for number 1. we're going to be looking at the list and see there's a 1 there. We're going to be counting them 1, 2, 3, 4, and so on and so forth. So we're going to use the code, Python code, to do that for us. And we can use the count method to count the instances of an element in a list. So the dice results is our list above there with all those numbers. When I apply .count, I can say count this number. And I'm counting the dice number being the variable in our loop. So the dice number is going to be 1 for the first iteration, then it's going to be 2 for the second iteration, and 3 for the third, and so on and so forth. The last iteration is going to be number 6. So this for loop is going to count all the occurrences of the different dice numbers. And in addition to counting the number of times they show up, I'm going to compute the frequency as well. The frequency being just the number of times they show up divided by the total number of elements in the list. And I'll print one step at a time. So let's run that. So for number 1, we got 9 times. So if you count there, there's going to be 9 number 1s there. For number 2, we got 6 times. For number 3, we got 12 times, and so on and so forth. So these are the counts, the individual counts for each of the different numbers in that results list. And the frequency is just was 0.15 for 1, which is 9 divided by the total, which is 60, and 0.10 for 2, which is 6 divided by 60. This frequency is represented as a ratio, but if it's convenient for you, if you are more used to thinking in percentages, you can think of the frequency in percentage terms, which is just this number multiplied by 100. So when the number 1 showed 9 times, that's a frequency ratio of 0.15 or a frequency percentage of 15%. And for example, the number 6 showed up 10 times, that's a frequency ratio of 0.17 and a frequency percentage of 17%. Now, at this point, I'll answer the question that I asked in the beginning. I'll leave it in even for more the end in case other people want to still correct or provide their answers for how many times should you expect to get each number. You see you got different times the different numbers because it's a random process, right? I'll answer the initial question in a moment. Before that, I just want to highlight something here is that this concept of frequency, or sometimes also called density, corresponds to the concept of probability. So the frequency ratio is always going to be a number between 0 and 1, and probability is also always a number between 0 and 1. And we'll see that that is going to be important for understanding the A/B testing. So keep in mind that this frequency corresponds to the concept of probability, which is, again, the number between 0 and 1, or if you prefer thinking in percentage, this kind of says that just based on this data, if you were to roll a dice again, one could expect the number 1 to show up 15% of the time, the number 2 to show up 10% of the time, number 3, 20% of the time, and so on and so forth. This is a fairly small sample, so this difference may be an artifact of a small sample. One should have done a larger sample, but this was just for the introduction purposes. And that's the table for counting the number of occurrences of the different dice numbers in the list, in the results list. We can represent this in a graphical form, and that's the histogram. So the histogram is the representation of this table in a graphical form. Indeed, this is the histogram, and I'll show both the table and the histogram at the same time. The histogram, you have the numbers at the bottom, the dice numbers at the bottom, and for each of the numbers, you have the count of how many times it showed up. So the number 1 showed up 9 times, and we get the bar with a height of 9, and then the number 2 showed up 6 times. We get a bar with a height of 6, number 3, 12 times, a bar with a height of 12, and so on and so forth. So that's the meaning of the histogram. The classical representation of the histogram is the count histogram, where it counts the number of occurrences of each value in the data set. There's also the frequency version, which instead of representing the counts, represents the frequency. So for the 9, represents 0.15. So the number 1, which was 9 in the count histogram, is 0.15 in the frequency histogram. The 2, which was 6 in the count histogram, is going to be 0.10 in the frequency histogram. So these two versions of the histogram, the count and the frequency, show you the same thing, just the general shape of your data. One of them represents the count, the other represents the frequency. And again, the frequency, sometimes also called density, corresponds to the concept of probability. So the height of the bars kind of give you the probability of the expected outcome of each of those numbers based on this data, which again was very limited data. So just based on this data, you could say that maybe this dice is not fair. the number of times, the probability for getting a 2 is smaller than the probability for getting the other numbers. And that's kind of a slightly higher probability for the number 3 and the number 5. But again, that's just an artifact of a small sample. But so the important points here, this is what an histogram is. And the histogram relates, well, you can have the count version and the frequency version. And the frequency version relates to the idea and the concept of probability, where kind of the height of the bar represents the probability of you getting that result if you do the experiment again. Okay? So that's an important concept for what's coming next. So I'm going to give you 5 minutes to this hands-on activity. I suggest you do this by just pen and paper, pencil and paper. If you want to do with code, feel free to do with the code. But I recommend that everyone does actually this manually. So now I would suggest everyone does this activity manually, and you can do it code later at home. So the goal is we have now this list of results from rolling a dice. Now it's just before I go there. So sorry, I forgot to answer my first question. So how many times would you expect a number 3 to show up in after you roll 60 times? So assuming that is a fair dice, each number should show up a 1/6 of the time, 1/6 of the times. 1/6 of 60 is 10. So assuming it's a fair dice, a perfect dice, each number should show up 10 times, and the number 3 should show up 10 times, the number 4 should show up 10 times, and so on and so forth. So that would be the ideal outcome. And as you can see, it's it's kind of around 10. And if we were to run this experiment with a higher number of rolls, you'd get more close to the ideal result. Okay, so that was the answer for the initial question. And now it's this activity for you to essentially reproduce what we just did, just with a smaller data set. Instead of 60 numbers, it's just 30, so that you can actually count this by hand. So you should produce the count table. You can do just the counts. You don't need to do the frequency. Do just the counts. And then from the counts, create the count histogram. Create this histogram for this data. So I'm going to leave the data up there. Given this data, your goal is to manually create this histogram. You can draw it by hand. And you have like 5 minutes for that. As you do the count, feel free to post your results on the chat. So the count's you have to count how many times does the number 1 show, how many times does the number 2 show, and so on and so forth. Feel free to show that in the chat so people can see if they're getting the same result. And after you do the count, you use those numbers to just manually draw the bar chart that represents the histogram. So I'm going to give everyone a few minutes to try to do that. If you finish the manually drawing the histogram, feel free to also write in the chat. Okay. 1 more minute. And then we'll look at the solution together. Okay, we have several people posting the results. Very good. So let's look at the solution together. So this is the list of the results. And I just have a simpler version here to create the histogram. So I'm going to create the table and the histogram at the same time, as we did just above. We're just reusing the code from above. I did not define our results yet. Go. So, and I can even print dice. Let's print dice results. Okay. Right. So this was our results, this list. And this is the count table. The number 1 shows 4 times, the 2 4 times, and so on and so forth. And number 6 shows only 3 times. And this is the count histogram. So again, for the number 1, we have a bar of height 4, because 4 is the count of the times the number 1 showed up. 2 is also 4. 3 is 7. And 4 is 6. 5 is 6. And 6 is 3. So that was the solution for the count table and the histogram. And now that we know what's an histogram, what it means, and that the frequency histogram corresponds to the concept of probability, we're going to move into A/B testing. Okay. All right, so this is going to be the main part of today's workshop. Okay. So A/B testing is an A/B test is an experiment to compare 2 competing options. They are often called A and B. That's where the A/B testing comes from. And the goal is to determine which of those options is better. I use the word options as kind of a general word. Options could be two treatments in the medical context, 2 different designs in the context of web designing or adverts, or 2 different products in product development, or 2 different prices in sales. Okay, so there are many options in many places, many industries where A/B testing is used. I'm using this word options, kind of a general term that can be used to describe all of those different applications. Now, important and key terms in A/B testing, because these A/B tests and hypothesis testing is so associated with, in particular, the medical industry. We often call them the treatment and no treatment or control group. So you'll often see the concept of treatment, and treatment is just something that we expose the subjects to, like in the medical context, a drug or a different some sort of medical treatment. In the web development, for example, the treatment would be a different headline or a different ad or a different price. Okay, and often we want to compare 2 options, and we often are working in an industry where something already exists. So there's already kind of a background, and you want to normally test if a new option is better than the existing option. So we call the existing the control group. So there would be the group with in the medical context, no treatment or a standard treatment. And the group to which we expose the new idea, the new option, is the treatment group. So treatment is something to which we expose the subjects, and often we use kind of the standard treatment or no treatment, the standard option or no option as a control group, and then the new idea, the new option, that the treatment to that what we call the treatment group. So those are the two groups that you can think of, group A and group B. One of them is going to be the control group, and the other one is going to be the treatment group. Now, we have to, another important concept is the randomization. So we use randomization to attribute different subjects to different groups in a randomized way to avoid any bias. So the randomization is the idea of randomly assigning the subjects to the 2 groups, so that we try to avoid include bias in our group selection. And our final goal is to determine which of these 2 competing options is better. So we need to have a way of measuring what's better, and that's the concept of a test statistic. So the test statistic is going to be the metric that you use to measure the effect of the treatment, so that you can say which group is better. Now, those are kind of the general key terms that are often used in A/B testing. let me highlight the important point. So the fact that we use, that it's important that we use randomization, because due to the fact that we use randomization, we'll be able to tell that any difference that we may find between those two groups, the group A or group B, or control group and treatment group, can only be done to two things: either random chance in the assignment of the subjects, sorry, corrected the typo there. So the fact that we use randomization lets us tell that any difference that we find between the two groups can only be due to two things: random chance in the assignment of the subjects. We are lucky or unlucky and put the subjects that in theory would perform better in one of the groups just by random chance, or there is actually a real difference between the groups A and B, the treatments A and the treatment B, the option A and the option B. So that's why it's important that we use randomization. It's due to that fact that we can say that when we do an A/B test experiment, the outcome can only be done if there's some effect that we can measure as the outcome. It can only be done to two things: either random chance in the assignment of the subjects, or because there's actually a real difference between the two groups A and B, the two treatments A and B. So that's an important point. Aside from the key terms, that's kind of the core of A/B testing. So we use randomization to assign different subjects to different groups. Those two different groups are subject to two different treatments, while everything else being equal. So the randomization is so that we can say those subjects in different groups for those subjects, everything else is equal. The only difference is the different treatments for group A and group B. That's the idea. So that we can say any difference we find, it's either a real difference that is due to the difference in the treatments A and B, or just random chance of the assignment. We were just unlucky in the assignment that we did. And that's an important point that we need to understand aside from the key terms. Okay? So some general examples of A/B testing are kind of related with what I mentioned above. For example, testing if two different therapies to determine which one is better or more effective at suppressing cancer. Normally, one of them is going to be the control, the standard one, and the second one would be kind of the new idea, the new therapy, to see if it's better than the already existing one that will be the control. Testing two prices to determine which of them provides a higher profit. Testing two web headlines, for example, a news article, testing two different headlines to see which of them leads to more clicks, or testing two different web ads to determine which of them generates more conversions. So those are kind of general examples that kind of cover most of the main industries that use A/B testing. A specific example, actually, from a large company, there's this story from Microsoft, in particular the Bing product in Microsoft, where through A/B testing, they were able to make a 12% improvement that led to more than 100 million revenue increase. And I have here the reference for you if you want to read the details about that specific example. So you can see what seems to be a fairly relatively simple test can lead to huge results, especially where there is a large scale effect, like a large company or a market or a product that sells a lot of volume. But we'll see that now as in an example. We'll use an example to explore more these concepts. So just introducing these concepts, just like that, it's very difficult to understand. So what we're actually going to do is to explore an example from scratch, and going to see all those concepts in action. Okay. We're going to use a web example. You can think of it as a web experiment. It could be an e-commerce experiment with where two option A and option B are, say, two different prices, or they are two different headlines, or two different web designs. So we'll just keep the general word option, okay? And we have subjects that are, we have two subjects, the group A and group B. So we have two groups, A and B, and we have groups of subjects to which we are randomly assigned to those two different groups, A and B. So we conducted the experiment, and we ended up having a total of 1,020 subjects going to group A and 980 going to group B. So you can do A/B testing even if the groups don't have the exact same number. That's perfectly fine. From those subjects in each of the group, Most of them did not convert, so there most of that's normally in web experiments. Most of them are not converting, but a few of them convert. Like say they bought the product, they clicked in a headline, they clicked in an advert. So for the group A of the 1,020, 100 of them converted, and from group B from 980, 90 of them converted. Now we can compute a conversion rate, and we're actually going to use the conversion rate to compute our test statistic. So we're going to use the conversion rate to compare if any of those groups is better than the other. So if we just compute the conversion rate with the data that we got from this experiment, the conversion rate is going to be 100 divided by the total, and that's rounded to 9.8%. So the group A had a conversion rate of 9.8%, and the group B had a conversion rate of 9.2%, which is 90 divided by 980 multiplied by 100. So those are the conversion rates. And what's the difference? 9.2 minus 9.8 minus 9.2, that's 0.6. So we have a difference of 0.6%. It seems small, but it could actually be meaningful and important in a high volume business. Now the question is it significant? Is it statistically significant or not? And we're going to show you how to do that now. So the whole goal of the A/B testing, when you find a difference between the two groups, between the two treatments, we have to understand if that difference is significant or not, so that we can say if it's just due to chance or if it's due to an actual real difference between the two groups. And I'm going to show you now how to find if this 0.6% is significant or not. Okay? So to start, let's actually put these numbers into variables so that we can work with the numbers. And variables are just another concept in programming. We use variables to store values that we need to use in our program. In this case, we're going to store the value 1020, which is the total number of subjects in group A, to a variable called A_total count. So it's the total count of subjects in the group A. Then the total number of subjects in group B is going to be 980. The conversions were, I'm going to call them AES count, AES for conversion, and BES count, so 100 for the group A and 90 for the group B. And then we can actually compute all the rest. We need to be writing it by hand. The ANO count is the non-conversions. The BNO count is the non-conversions for B. And we can compute the percent conversion. And we can finally compute our statistic, which is going to be the difference between the conversion rates in percentage points. So I'll be using here percentage points just for convenience, because the numbers are small. At least with percentage, they are a little larger. And it may be more familiar for you to look at percentage numbers. So we have those numbers. And again, we can reproduce what was above. So the conversion rates for A was 9.2, for B was for A was 9.8, for B 9.2, and the difference A minus B is 0.6%. So our test statistic is the conversion rate difference, which we observed as being 0.6%. Now the question is this significant or not? Is 0.6% a significant difference in the context of this problem? We're going to see how to do that now. Normally, you do a A/B test by using the knowledge of the theory of statistics. You know what the theoretical distribution underlying this problem. You'd use that knowledge to directly compute the p-value and determine from there. But I'm not assuming you know theoretical statistics. So we're going to do this from scratch by using resampling, and in particular, one resampling method, which is the permutation test. And I'll introduce this, tell you the steps. And this is essentially just counting things and resampling things, putting things in a bag and taking things out and counting them out, so that we can make an estimate of what would be the expected variability for this problem. So we want to know if this difference is significant. What we're going to do is kind of simulate this experiment many times, and each time determine what would be the difference from that simulation. And we're going to get many numbers that would equivalent to this difference. And then we're going to compare this difference that we actually observed from our experiment from all those numbers that we got from our simulations. And if this number here is much larger than the expected numbers in our simulations, then this is real. If this number falls within the numbers that we see in our simulations, then we can say that this is just due to random chance and it's not a real effect. So that's the idea. And I'm going to show you step by step how to do that. So resampling is the process of repeatedly sampling values from an observed data set to determine the random variability within a statistic. And that's what we're going to do right now. So there are different methods of resampling. There's one in particular, this permutation test that we're going to do now. These permutation tests is a resampling procedure that's particularly useful for hypothesis testing. And that's what we're doing here. We have two groups. We measured the conversion rates in each of them. We saw the difference between the two of them. And now we are testing if either of those two groups is better than the other. So in more detail, the permutation test is the process of combining those samples, those data samples. In this case, we only have two. We're going to combine them together and random shuffle them and random resample from them new samples and compute the metric again and get the new differences, and from those determine what would be the expected variance variability in that metric, so that we can compare the metric that we actually observed with that expected variability. And we're going to do this permutation test step by step. These are the steps, and I'm actually going to explain them step by step with the code and with the outcome as well. So the first step is we got these two groups, right? With the subjects in group A and subjects in group B. In each of those groups, in A, there are people that converted, there are conversions, and there are people that did not convert, no conversions, and the same thing in B. Just different numbers, but in each group, you have conversions and non-conversions. What we're going to do is represent conversions by a number, say the number 1, and the non-conversions by the number 0. And so you're gonna then get those numbers, the ones for conversions, zeros for non-conversions in group A, and the ones and zeros for group B, and put them all together in a bag. So now we have a bag that has all those numbers, all the data from the two samples. And the next thing we do, we're gonna shuffle the bag to randomize the bag. And then we're going to draw new samples. So we're gonna draw a sample, that's gonna be step 3, a sample with the same number of items as the number of people in group A. So imagine now we have a ball with a bag with many balls as there were subjects both in group A and B. And now we're going, in the first sample we're gonna take as many balls as there were in group A, and that's gonna be the new resample for group A, like simulating again a new group A from this randomization process. And then the fourth step is actually take a sample of balls with the number of balls being the same number as the number of people in the group B. And that's gonna be a resample for group B, like a new sample of group B. And then step 5, we're going to compute the statistics for each of those new samples. And we're going to compute the difference, and we get a new value, a new difference between those two groups. So we get this was our observed difference. And what we are doing now is over and over compute new values for this difference by simulating this random process, by using this permutation process, so that in the end, we can look at all those simulated numbers, all those numbers from our permutation process, and compare this single number here that we actually got from our experiment to all those numbers. That's the goal. And this is the process. So you put all the data in the bag as if they were balls with ones and zeros, and then we shuffle the bag, and you take samples from with the size of the group A and samples with the size of the group B, and then you put everything back again, and you repeat the process. Samples for group A and group B, compute the metric, and put everything again, and so on and so forth. And you do this many times, a fairly large number of times. For example, about 1,000 times should be sufficient for you to have the distribution of the expected difference between those groups. So each time you do this, that's a permutation. So that's the concept of permutation, is changing the order of things by putting all the data in the bag, and then resampling, taking new samples, and from those samples computing again the statistic that we are interested in, which is the conversion rate, and in particular the difference between the conversion rate in the two groups, and do that over and over so that we can get those values many times, and we're going to use those many values to look at what would be the expected variability in that statistic. So I'm going to show you the code. First, I'm actually going to run the code and show the output step by step so that we can see those steps in action one at a time. And I'm going to run just a small number of times first. So I'm not going to print the steps 1,000 times. I'm just going to run it 2 times. And I'm going to explain, before I explain the code, I'm going to show you the steps. Okay. So step 1, we want to create a bag with all the data. So just putting all the data in the bag, no shuffle yet. The shuffle is coming in step 2. what was the data that we had? Originally, we had a total of 190 conversions, group A plus group B, and a total of 1,810 non-conversions. So our bag is going to have 190 balls with the number 1, essentially a list with 190 ones. And then in addition to those 190 ones, is also going to have 1,810 zeros. So there's going to be a total of 2,000 balls in the bag. That's all the data from the original experiment with group A and group B. We're going to have 2,000 balls. Of those 2,000 balls, 190 are balls with the number 1. All the rest are balls with the number 0. So we put all these balls in the bag, and we first put the balls with number 1, and then we put the balls with number 0. So if you look at the first balls in the bag, say these first 20 or 30 balls, they are all number 1 because we put the number 1s first, okay? And if you look at the last balls, they are going to be all number 0 because we put them last. So at the moment, we have all the balls in the bag, but they are very neat. So what we're going to do, the second step is to actually shuffle the bag. And this is going to be, that was just the setup. That was just creating the bag with all the data. And the bag is very neat, so we're going to need to shuffle it. So the first permutation is going to be this one, and then going to be a second, and so on and so forth. We're going to go step by step for each of the permutations. So the second step, we're going to shuffle the bag. The bag was very neat. If I shuffle the bag and I show you now the first balls in the bag, you'll see that while before, when it was very neat, all the first balls were 1. Now we have mostly zeros, but we also have 1s and 0s and 1 and 0. So now the bag is shuffled. So the bag is randomized now. That's step 2. Shuffle the bag with all the balls in it. Step 3, draw a resample of the size of the group A. The size of the group A was 1,020 people. So we're going to get 1,020 balls. And we're going to check how many ones did we get in those new 1,020 balls. And it so happened that we got 92 ones of those 1,000 and new 20 balls. Okay? So the step 3 is to make a resample of the size of the group A, which is get 1,020 balls. And then we count how many of those are ones, and there are 92 ones in that new sample of 1,020. Step 4 is to do the same for the group B. In this case, we only have 2 groups, right? So if we take 1,020 balls for the group A, the balls that are left in the bag are going to be 980. So that's going to be the resample for group B. But you can see the idea of if you have many more groups, you make a resample for group A, then you go to the bag, a resample for group B, and then for group C, and so on and so forth. And at the end, you're going to be left with whatever is for the last group. So in this case, we do 1,020 for group A, and then we're going to do 980 for group B, because that was the original number of people in group B. And we count how many ones that we had there. And just so happened that in this permutation, we had 98 ones in those 980 balls. Okay. Step 5, we record the difference. So the conversion rate for group A is going to be 92 divided by 1,020. That's 9.02. And the conversion rate for group B is going to be 98 divided by 980, and that's 10%. That's 10. Okay, 10%. And now we compute our statistic, or test statistic, which is actually the difference between the conversion rates, A minus B. And now A minus B is minus 0.98%. So that was one permutation. And now what the process does is does this over and over again. Now we're going to do the second permutation, and second permutation again, step 2. We're going to, so imagine that after each permutation, we put all the balls back again in the bag, okay? So before the next permutation, all the balls go back in the bag, and then we shuffle the bag. And now you can see that this new shuffle is even different from that initial shuffle. So here we have a 1 here, we have 1 there, we have a 0 there. So the bag is shuffled again. We resample for the group A, again, get the number of balls that's the same as the number of people in the group A in the original experiment, count the number of ones in that new resample, and now we got 93 ones. In the previous permutation, we got 92, now we got 93. Then you do that for group B, we get 980 balls for group B, and now we got 97 balls with number 1 for group B, while before we got 98. And we compute the conversion rates. Now for group A is 9.12, now for group B is 9.90, and we compute the difference between those two numbers with the difference between the conversion rates, and we got minus 0.78. So that's the process. That's the permutation test. You do many permutations, but each of them is the same thing. You have the balls with all the data in the bag. There's balls with number 1 that were the conversions, balls number 0 that were non-conversions. So 1s are successes, 0 are failures, 1 are conversions, 0 non-conversions. You shuffle them and you resample, you get samples of the same size of the original groups, and then you compute the matrix again. And you do this over and over. As you can see, every time you do, we get a new value for this difference. And if I run these 1,000 times, I'll get 1,000 of those values, which then I can use to look at the variation in those values. So, okay. I'll just go briefly to the code. The code is long because it has a lot of print messages to show you the steps in action. But if I were to remove the prints, it will become much shorter. So what we are doing here is in the beginning, we are setting a random seed so that this again is reproducible. I'm going to set a number of permutations. I just did 2 now so that I'll show you just the 2. Afterwards, I'll actually be doing 1,000 permutations, okay? This AB resample yes % difference is going to be our array that's going to contain the test metric values, the difference between the conversion rates between group A and B. And this is just to control if I want to print the message or not. So this is a if-else construct in Python. If this is true, if the number of permutations is smaller than 10, I set the variable verbose to true, and I'm going to use verbose to say print the messages or do not print the messages. So when verbose is true, I'll be printing all those messages. When verbose is false, I will not be printing the messages. And I do that because I don't want, for 2, I want to print all the messages to show it to you, but I don't want to print 1,000 messages. It will become very long, okay? So step 1, put all the balls in the bag. So we're going to have ones that represent the conversions, and the number of ones are going to be the number of conversions from A plus the number of conversions from B. And the number of zeros are going to be the number of non-conversions from A plus the number of non-conversions from B. This creates a list with those number of ones, and this creates a list with those number of zeros. And I'm putting the ones and the zeros, putting them together in a new variable that I call the bag. So now the bag contains all those balls with the correct number of ones and the correct number of zeros, but I inserted ones first and the zeros next, so it's very neat, very organized. So the step 2, we'll have to shuffle it so we create some randomization. Okay. And we have, so this is just printing the message about our setup, the message that you just saw before. These sets, I'm creating these sets, which are going, these all sets are going to contain an index for all the bag, the balls in the bag, so that I can actually pick the balls by the index. That's just a convenience to work in Python. I'm going to do set operations when I pick a set for the group A, the remainder set is going to be directly for group B. It's just for convenience. Okay, it's just a way of pointing to the balls in the bag. So now we need to do the permutations over and over. So I'm going to use again a for loop to repeat the same thing over and over. So this highlights here as step 6 because the step 6 is doing the steps 2 to 5 many times. How many times? The number of permutations. So the number of permutations contains the number of times you're going to repeat the process. Step 2, we shuffle the bag, and there's a convenient shuffle function in the random package that shuffles a list. So that's the shuffle is going to shuffle the list in the bag, and it's going to create randomization in the bag. Okay. So step 3, we want to select a sample the same size of the group A. So we can use the sample function in the random package. We're going to sample from the whole set. The whole set again are indexes that refer to all the balls in the bag, and we're going to get us a sample with the same number as the A total count, which is the number of subjects that were assigned to the group A. So the A set is going to be references, a set of references to the balls in the bag, a random set. Okay? And then we can use that set to select the balls from the bag. So the A resample is going to be a collection of a list of zeros and ones, which represents the balls that we just took from the bag for the group A. And the number of balls is the same number as the number of subjects that were initially assigned to the group A. Step 4, now we only have 2 groups. So whatever balls are left in the bag, if I were to pick them, I would have to pick them all, but I'll just say the difference, whatever is left in the bag is for group B, because there are only 2 groups. So that I use the set difference to make the difference between all the sets, all the numbers that refer to all the balls in the bag, to the difference for the A set, the numbers that refer to the specific balls that we took for the A set. That difference refers to all the balls that were left in the bag, and with that, I assign them to the B resample. Okay? the final step is to compute the matrix. So we compute the conversion rate for the group A in this new resample, okay, in this new sample that from the permutation process, and then we compute the conversion rate as percentage for the group B, and we compute the difference. And the difference is our test statistics, so we're going to append that AB difference to the list that's going to contain all the values of the difference between the conversion rates. So this list, the AB resample yes percent diff, is going to contain all the values for our test statistic. And that's how we got this output. And I went now through the steps to the output and through the code. So now let me run this 1,000 times so that we can get the result to proceed. So now it's computed 1,000 times, okay? We got 1,000, we did 1,000 permutations. Each time we got a new number for our test statistic. And now we can look, for example, at the first 20. And we can see here that we got a variety of numbers that represent that test statistic for those permutations, for those resamples. And we can now look at, this was our original statistic from the experiment that we did. From the original experiment, the original difference was 0.62. And now what we want to know is, how does this 0.62 compares with all these numbers? Not just these 20, but all the 1,000 numbers that we got from our permutation test. Now is where the histogram comes in. So you remember that the histogram is a tool to represent, to summarize our data set, in particular, to summarize the distribution of our data set. We're going to use the histogram to create the distribution of those 1,000 numbers. So we're going to create here the histogram. And now in blue is the distribution of those 1,000 numbers that we got from the permutation test. And that gives you kind of the expected variability of our test statistic, which is the difference between the conversion rates. So this is what we'd normally expect just by a random chance, okay? This is what we'd normally expect. And now where is our 0.62? Our 0.62 is here represented by the red line. Here is 0.6.62, okay? So now we see that before we did this, we just saw that we had a 0.62% difference between the two groups without any reference whatsoever. And it looked small, but we couldn't say anything because we had no reference. Now what we created, we simulated that same experiment many, many times by using just the original data to get an idea of what would be the expected variability in such a metric. And the expected variability is represented by the histogram in the back, the blue. So we expect the numbers just by random chance to be within that shape, within that histogram. Our number, that we got, the 0.62, falls well within that expected variability. So just by looking at the graphic, we can say that the result we got is most likely due to chance, and it does not reflect a real difference between the two groups A and B. So whatever we had, maybe the two different prices, the two different headlines, the two different ads, they are really not different, even though it looked like they had some difference between the two of them. Okay, so the important point is we did the permutation test to get that histogram that represents the expected variability in this problem, and now we can compare the value that we actually observed, this red line, and we can see where it falls. If it falls within that histogram, within that distribution, then it's more likely that it's just due to chance, and there's no real difference. Okay, so with this we can make with this graphic we can make kind of a intuitive decision just by looking at the graphic. Okay? But we can also compute the p-value. Let me just show you. Okay, let's do the p-value. So what's going to be the p-value that you've heard? So what would be a way? We did this just by looking at the visualization, right? So it was just a visual inspection. That's kind of a qualitative measure. We want a more quantitative measure. And intuitively, what do you want the line to be? What we want this red line to be far from the distribution, to be away from distribution, so that it would be away from the expected variability. A way of computing, making a quantitative measure to describe that is, okay, so what's the area that is in here? So consider that our hypothesis was that A was better than B. So we were expecting the red line to be far to the right, for example. What is the area underneath here on the right hand side? So that area on the right hand side, again, recall that the histogram represents the histogram is akin to the concept of probability. So the area in blue, the whole area in blue is 1. That represents the total probability. The area on the right hand side of the red line is going to represent the more extreme values that there are, the probability of getting a more extreme value than the one we got. So let me actually compute that so it's easier to explain. So what we are doing here, we are computing, checking what are all these numbers here that are on the right hand side of the red line. And with all those numbers, we are computing this area. The area on the blue area are on the right hand side of the red line. Okay? And what we find is that from all those 1,000 numbers, so the histogram, the blue histogram is being represented from those 1,000 numbers that we got from the 1,000 permutations. 347 of them fall on the right hand side of the red line. So there is 347 on the right hand side here. So you can see that there's quite a lot that are still higher than our red line. And that gives you a ratio of 347 by 1,000 of 0.347, about 0.35. So about, if you think about percentages, about 34.7% or 35% of the values that we got from a permutations test are actually higher than the one we observed in our experiment. So that's a more quantitative way of checking if the value we got is significantly different from the values we would expect. And what we are seeing here is that the value we got is smaller than about 35% of the values that we'd expect in the model. So this area here represents 35% of the probability, and when we compare it with our red line, it shows that one would expect about 35% of values to be higher than the one we observed. So the one we observed is well within the variance of the expected values, and that difference that we observed in that single experiment is due to chance, and it's not due to a real effect between the two groups. Okay, so let me consolidate these concepts by mentioning them in the context of hypothesis testing. So this quantitative measure that we computed here is actually the equivalent of the p-value. Computing this area, the area that is left of the more extreme values than the observed ones, than the one that we observed, that's the concept of the p-value. Okay, and let me just introduce the concept, and we can come back and look at it again. So before I introduce it, let me show you an example where these would actually be significant. So if we've had a higher difference in the beginning, so if you had still 100 conversions in the group A, but less conversions in the group B instead of 90-70, to make the relative difference between the two groups higher. And if we reproduce this, here. Now, if we reproduce this, our observed value, our statistic was there is a about 2.7 difference between the two groups, because now one group was 100 and the other 70, while before the group B was 90. So we made the difference larger between the two groups to see if that larger difference would be significant. And now you can see that this new observed value is more away from the expected variability. Now it's more away from the distribution, from the center of the distribution. And if we compute how many numbers there are there from our permutation test that are higher than our observed value, the red line, there are only 27 in the 1,000 that we got. There are only 27 numbers there that are higher than the observed value. So that corresponds to what would be a p-value of 0.027 or 2.7%. And if you were, then that you could say that would be significant because the observed value is very, very far from the expected value. So the red line is far from kind of the center of the distribution. And you could say that now it is due to a significant real effect in the two groups and not just random chance. Let me just introduce the concept of p-value to make that more clear, hopefully. So all we have been talking about A/B testing. A/B testing is an example of hypothesis testing. So I just want to bring you to the more general concepts in hypothesis testing. So hypothesis testing or significant test is used to determine whether random chance is responsible for observed effect or if there's a real effect. Again, the same thing we have been doing for A/B testing. Now, more formally, when you are doing a hypothesis test, you have two hypotheses, the null hypothesis and the alternative hypothesis. The null one is that all you are seeing is just due to chance, okay? There's no significant real difference. Any observed effect is just due to random chance. The alternative hypothesis is the opposite, and that's what you would want to prove. In our case, the null hypothesis that the difference that we saw in your A/B test between the group A and B, it's just due to random chance. And the alternative hypothesis that no, it's not due to random chance. There's actually a real difference there and a significant difference. Okay? So hypothesis testing is, so let me highlight, so that's the definition of null and alternative hypothesis. Let me highlight the important points aside from the definition. So what the hypothesis test does is that it assumes that the null hypothesis is the true one. So when we're doing a null hypothesis, we assume that the null one is the true hypothesis, that there is no real effect, that is just due to chance. And then our goal is to disprove the null hypothesis. So, and in particular, the hypothesis test is going to assume that the null hypothesis is true, and it creates a null model, a probability model, and tests whether the effect of your observed difference is a reasonable outcome of that model or not. So that null model, okay, and the null hypothesis is that the logic construct that represents that notion of nothing happened, and that any effect that we are seeing is just due to random chance. So this here, the null model, that probability null model, is the one that's represented by the histogram. Okay? So this histogram that we got from our permutation test is the representation of the null model in the null hypothesis that says nothing happened, anything that you are seeing is just due to chance. And this is a graphical representation of that null model. Okay? So when you see hypothesis testing and null hypothesis, this permutation test is a good way of doing it from scratch and to actually put a visual representation of what a null model is from just doing permutation tests on the data without using statistical theory. So what we have here is an hypothesis test where we're testing two groups, A and B. We are testing if one of them is better than the other. In particular, we're going towards the direction of is A better than B? And we need a null hypothesis of what the expected difference in this problem. And we do the permutation test to compute this null model, this probability model that represents the null hypothesis, and the red line is what we observe. If what we observe, the red line, is very far from the null model, then it's a real effect. If the red line is very within the null model, very within this representation of the null model, then it's not a real effect, it's just due to random chance, okay? So we build a lot step by step. We looked at, try to understand what's an histogram, and that it corresponds to the concept of probability. And we did the permutation test to create an histogram that actually now we know represents the null model, the null hypothesis that any effect we see is not real, just due to random chance. And now we know that if what we observe, the observed effect, the red line, is very far from that null model, the blue distribution, then it's real. It's a real effect. If the red line does not falls within, very close within that expected null model, then it's not real, just due to random chance. So that's the core of A/B testing and hypothesis testing, represented in a graphical way and built kind of from scratch by using the permutation tests. Okay? So I hope that highlights these concepts, and we had to build, again, step by step. So just a few more points about the hypothesis testing and these concepts of p-value. So the p-value is the area, in this case, of the ratio of values that are higher, more extreme than the observed one. So the p-value here is the area of this histogram, this part of the blue histogram that is higher than the red line, the observed line. Okay? So the definition of the p, normally the people define the p-value as just the second part here, and they forget this, the first part, which is the assumption. So normally you'll read and you'll hear people saying that the p-value is the probability of obtaining results as extreme as the observed result. That's true, but with the given condition. The given that that's the definition of the value given a chance model that embodies the null hypothesis. Okay, so you cannot just say that the p-value is that. The p-value is that for the given null model from the null hypothesis. And here we represent in a graphical way the null model that represents the null hypothesis. And that's why when it says the p-value is the probability of obtaining results as unusual or extreme as the observed ones, that's why I'm telling you that the p-value is the area here, because these are the values that are as extreme or higher than the observed one, which is the red line. Okay. So I hope that highlights the definition of the p-value. It's contingent to the model of the null hypothesis, the chance model of the null hypothesis, which is here represented in blue. So normally when we do this, we have to set a threshold for what's going to be, what are we going to consider unusual or extreme? What level of probability or what level of p-value do we consider unusual or extreme? Like in this case, we got a p-value of 2.7. Is that unusual, extreme, or not? So what the standard practice is to actually, before you even do the hypothesis test or the A/B test, you define an alpha parameter, which is a threshold, a probability threshold for what you classify as being unusual or extreme. Normally, people use 0.05 or 5%. Okay, so that's the same. The 0.05 just represents as a ratio, the 5% or probability, and 5% just as a percentage. Now, these must be defined in the beginning of the experiment before you do it, so that you cannot, in the end, adjust the p-value to make it significant or not. Okay, so we have this alpha. So if we assume that we had in the beginning an alpha of 5%, and with this experiment we did just now, we got a p-value of 2.7. The 2.7 is smaller than the 5%. Then we say that this p-value and the observed data is more extreme than we're expecting. And because of that, it reflects a real effect between the two groups, A and B, and it's not just due by chance. So kind of the rule of thumb is, if the p-value is larger than the alpha, we have to retain the null hypothesis, which was the previous example, and we conclude that the observed effect is just due to chance. If the p-value is smaller than the alpha, then we can reject the null hypothesis, and we can conclude that the observed effect is real, significant. So this is the case that I have in that example above there. If we assume the p-value was 5% at the very beginning, now we get a p-value of 2.7. The p-value is smaller than the alpha. We reject the null hypothesis, and we can say that there is a real significant effect. Okay? And again, the p-value is this area of values that are more extreme than the observed value, the red line. Okay? And just to show you that's the case. That's a case where the p-value was smaller than the alpha. If I show you the initial case, which was the one we started with at the very beginning, where the difference was not so big between the two groups. So if I show you here the initial case where the group A had 100 conversions and the group B had 90 conversions, we saw before that it was not significant, and I'll repeat that for you now that we know more about the p-value. Okay, so with this, in that condition where the number of conversions for the two groups was 190, now we see that just graphically the red line falls within this null hypothesis model, the expected variability for this statistic. Okay, and you see that the area of the values that are much higher, that are higher or more extreme than the observed one is very high. Indeed, it's about 35%. So the area, the blue area after the red line is about 35%. And so if you assume that if you started the test with an alpha of 5%, we have a p-value of 35%. 35% is much higher than the alpha. So we have to retain the null hypothesis. We are not able to disprove the null hypothesis, and we have to conclude that the observed effect is just due to chance. It's not due to a real significant difference between the two groups. Okay. I'm running I think we're okay on time. Okay, so this does not guarantee that your conclusion is going to be perfect, even within this. So this is kind of a statistical method for try to prevent you from having bias and to have a quantitative way of trying to determine if the observed effects that you are seeing are actually real or just due to chance. Still, you can still make errors, even if you follow, in the end, you can still have an error, okay? There are two types of errors, type 1, which are false positives, and the type 2, which is false negative. So false positive is saying that there's a real effect when it's just due to chance, and the false negative is saying that there is no effect, or that the effect is just due to chance when there's actually a real effect. So in this case, here we concluded there's no effect because the observed value falls well within the expected variability. However, if sometimes we don't know the real true, right? But if for some reason we knew the real true and we knew there was a real difference here, this would be a false negative, because we are saying there's no effect, but if there really was, then this would be a false negative. We are saying there's no effect because we got a p-value that was much larger than the alpha threshold we set, 35%, much larger than 5. That's what the method leads us to conclude there's no effect. But if there was, like, if we were able to have the true knowledge and we truly knew that there was a real effect, then this would have been a false negative, where we say it's a negative result, there's no effect, when there actually it was. And the false positive would be for the other case where we actually found, got to the conclusion that there was a positive effect, a real effect. So I'm going to repeat the one with the real effect according to the statistical test. Okay. So in this case, we are led to the conclusion that there is a real effect because the p-value is very small, at least smaller than 2.7, smaller than the 5% threshold we set at the beginning. So here we'd say there is a real effect. However, if again we knew the true knowledge and we knew there was no real effect here, this would have been a false positive. We are saying there's a real effect. We are providing a positive result, but in reality there was not. If we knew that there was not, we would know that this would be a false positive. So even with this, it's still possible to make errors. Now, we use this to kind of minimize our chance of creating errors, right? We use small thresholds to try to minimize the probability of making any of those errors. Okay? And in this case, the alpha is also the threshold that we accept to commit an error. Okay? So it's the threshold that we establish for what's unusual, what's extreme, but it's also the threshold that we accept to commit an error. Right. So that was A/B testing done from scratch with permutation tests without any knowledge. I never mentioned normal distribution, binomial distribution, because at the beginner level, if you don't have experience, if you don't have knowledge of statistics, I think that would be confusing. If I were just to say this is a binomial distribution, this is the p-test you apply to that, you'd not understand the concepts behind it. So here we actually, by scratch, we're actually to create a visual and graphical representation of the null model, the null hypothesis, and see how our observed value compares with that null model of the null hypothesis, and see that the p-value is the area of the values that are higher, of the values in that null model that are higher than the observed value. So you get a graphical interpretation of the concept of the hypothesis testing, and in particular the concept of the p-value, which is sometimes misunderstood. And again, remember that the p-value is contingent to the model of the null hypothesis, here represented by the blue distribution. Okay? Indeed, it is the probability of the values that are higher than the observed ones, but it's the probability of those values in the null model. Okay? That represents the null hypothesis. The null hypothesis being there is no difference. Okay. So to finish, let me just introduce you to the multi-arm bandit. Okay. We may go maybe a few minutes over. Just a few. So the multi-arm bandit is kind of a more modern, so the A/B testing is a quite classical statistical test. Okay? The multi-arm bandit is a more modern generalization of A/B testing. And actually is an example of reinforcement learning, and I'll tell you in a moment why. So it's a generalization of A/B testing for two reasons. First, you can use it to test more than just 2 hypotheses. You can use it to test A, B, C, up until n hypotheses. In addition to that, it lets you exploit your results along with the testing. So with A/B testing, you define a test in the beginning and you run the whole test. So you have to direct your subjects to the different option or B. You wait for have all the subjects, collect all the results, and then you compute the test statistic and you see if it's significant or not. So you have to wait to get all the subjects, all the results from all the subjects, and we have to wait a bit to get all the data. Once you have all the data, you compute the test statistic and you determine if the result is significant or not. Is it a real result, or is significant, or just due to chance? And when you determine that, you get your conclusion, you're going to apply that. In that case, for example, if you determine that a price A is better than price B, after you do the testing and you determine that, then you can go change in your product page, you put the best price, okay? Or if you determine that the headline is better than the other, then next time around you can use the next headline. But you have to wait until you finish the testing, until you collect all the data and you perform the testing. With the multi-arm bandit, not only can you test multiple options, but as you test, you can explore the best option. So with A/B testing, you all know the best option at the end, and then at the end you can go apply that knowledge to your problem. With multi-arm bandit, as you test the many options, you test also which one's performing better at any given time, and you can direct your subjects or clients or customers to the one that's performing the best. Okay, so those are the 2 levels of generalization of the multi-arm bandit. You can test more than just 2 hypotheses, and more than that, you can exploit the best hypothesis as you go along with the testing. You don't have to wait for the testing to finish for you to make a conclusion and then to go apply it. No, you can exploit the best options as you go along. Okay, and in that sense, it's an example of reinforcement learning, because you are learning at every step what's the best option, and at every step you can adjust the way you direct your subjects, your clients. You can direct more of them to the best option while still keeping some of them going to the other options, which at the time indicate as not being performing as well. Okay. Now, the multi-arm bandit name comes from the slot machine analogy. The analogy being that the one slot machine with one arm, because normally it's just most of the people just lose money there. It's called like a single arm bandit because you just lose money. The multi-arm bandit would be like a slot machine with multiple arms, each of them providing you a different return. Or you can think of it as one slot machine with multiple arms, or many slot machines, each of them with one arm that you can play around with the different slot machines. Okay, so you just have multiple arms, and each of them provide you different returns. Say in one slot machine, there's one arm that very frequently gives you like a 1 cent return, and then another arm that occasionally gives you like a $5 return, and then there's say a third arm that once in a blue moon gives like $1 million return. Now the question is, say you have like 1,000 coins to play in the slot machine. How would you assign those 1,000 coins to the different arms? Are you going to put all of them into 1 cent, frequently 1 cent, all of them in occasionally $5, or all of the coins in rarely getting 1 million? Or how do you split them? So that's the purpose of the multi-arm bandit algorithm. How to better split the coins in this case, or how to better split the clients to different options so that you can test those different options at the same time and in real time reassign the clients or the subjects to the ones that are giving you a better return. Okay, so I'm going to tell you this kind of a simple algorithm to do a simple version of the multi-arm bandit algorithm, and we're going to finish there. Okay, so just a few more minutes as I explain this version of the multi-arm bandit. So this version is called the epsilon greedy algorithm because it has this method as only one parameter called epsilon, and that epsilon is a number between 0 and 1, and typically is a small number, and you'll see why. So the way, let me show you how would we do the epsilon greedy algorithm for the A/B testing that we did just before. Okay, so it has very few steps, and you'll see how it relates to A/B testing. So on step 1, we generate a random number between 0 and 1, and you can call that random number R. Okay, and we compare it with epsilon. So epsilon is normally it's a number between 0 and 1, and it's typically small. So if R is smaller than epsilon, so remember epsilon is small. So if for R to be smaller than epsilon, it's not going to occur most of the times. So it's going to be a more rare event. So if it's smaller than R is smaller than epsilon, then we just do the normal A/B testing. We do flip a coin, 50%, 50 probability, and if you get heads, you assign to option A. If you get tails, you assign to option B. So if we get a small R, smaller than epsilon, we just default to the normal A/B testing. You just send the same number of people to the two different options. Okay? But if R is equal or larger than epsilon, then you direct the next person to the option that's being performing the best. Okay, so we have this epsilon, so that when we create a random number between 0 and 1, if that number is smaller than epsilon, we do the normal A/B testing. If that number is larger than epsilon, then we do the greedy approach. The greedy approach being assign that new person, that new subject, that new client to the option that performs better, the one that gives us the best return, or assign your new coin to those of the three arms that have been giving you the better return so far. Okay, so that's an example of a multi-arm bandit algorithm, the simplest one, the epsilon greedy algorithm, and that's the application for A/B testing. And you can actually see if, when epsilon is equal to 1, this reverts to just a simple A/B testing, right? So if epsilon is equal to 1, your random number is always going to be smaller or equal to 1, and you're always going to be doing the A/B testing. Okay, so this epsilon greedy algorithm is kind of see how it is a generalization of A/B testing, introduces a greedy portion through the epsilon parameter. So sometimes performs the basic, the classical A/B testing. Other times is going to use the greedy approach of directing the new clients to the best performing option. Okay? And it's the generalization for multiple options. What here in step 2, instead of using a coin, we just do a more general random selection. So again, the first step, you generate a random number with R between 0 and 1. You compare it with the epsilon parameter. And now you see if R is smaller than epsilon, then you just do a random selection between the n different options, the n different arms, and with the same probability for each of them. So just equal probability to pick any of those two of those options or arms. If the R is equal or larger than the epsilon, then we do the greedy approach. Direct the new client, put the new coin in the option or the arm that has been performing the best. Okay, so that's how you can do the testing and do the exploitation at the same time. So at the very end, you're going to have all the results, but at each step, you're actually evaluating the results up until that step to see what's the best option, and using that to direct some of the new coins or the new clients or the new subjects to the best performing approach, to the best performing arm or option at that time. Okay? So that was an introduction to what is the multi-arm bandit algorithm, how it is a generalization of A/B testing and a type of reinforcement learning, and actually in more detail, one type of multi-arm bandit algorithm, which is the simplest one, the epsilon greedy algorithm. Okay? So that's the end. If you want to learn more in particular about these A/B testing concepts, I recommend this book, which I actually used quite a lot to prepare these materials. You already heard about our bootcamps, so you're going to have here also the information about our bootcamps. There's a deadline on this Friday. If you want to look at the different bootcamps that we have and apply, you can follow these links. And if you apply by June, by the deadline, you'll have a 10% discount. So now let me open to Q&A and let me look at the questions. Okay. All right. So it's open to Q&A now. Let me know if you have questions. Oh, I see. I'm not seeing. I'm trying to look at the chat. Okay. Oh, if it's better to resample with or without replacement. So in this case, it's better without replacement. It's just convenient actually for hypothesis testing. It's more convenient to do without replacement. You saw that without replacement, what was left in the bag was for the second the second group. So it's convenient. So what are we simulating by doing the sampling with replacement? So before, if I do sampling without replacement, what I'm doing is I'm making sure that I use all the subjects that were used in the original experiment, right? Each ball in the bag represents a subject. So if I do without replacement, I will be using all the balls for the resampling, okay? If I do with replacement, what we do is that you take a ball, you look at it, it's 1 or 0, you make a record of it's 1 or 0, you put the ball back in. If you do that, if it's possible that it's quite likely that some of the subjects will not be used, okay? So doing with replacement, you will not ensure that you use all the subjects, and yeah, and without replacement, you ensure that you use all the subjects. Okay, so you'd want to do with replacement if you want to also randomize the selection of the subjects from the population. Okay, in this case, for hypothesis testing, is more convenient to do without replacement. Yes, Thompson sampling. Yes, so Thompson sampling is another method for the multi-arm bandit. Okay, I showed you here the epsilon gradient, which is the simplest one. The Thompson sampling would be difficult to explain here because it relies on Bayesian statistic. So I try to do everything from scratch here, try to avoid to use statistical theory, but Thompson sampling is a more elaborate method for doing the same thing as we are doing here. So it's a more elaborate approach for the multi-arm bandit algorithm. It uses Bayesian statistic. Okay. So that was on Thompson sampling. Okay, so I covered the question about replacement and non-replacement, the question about Thompson sampling. Is there others? I'm trying to scroll the chat. I'm going to share these notes. Yeah, so I already shared the link where you can get a version of this notebook. And I'm going to share you, actually, the one I shared initially did not have the solution for the hands-on, so I wanted you to try it. So we'll be sending you this notebook with the solution as well. So you're gonna get a new, there's a link that you got by email and also on the chat where you could get the initial version of this notebook. And after the workshop, we'll be sending you an email with the new this version that includes the solution for the hands-on work. Someone is asking why wouldn't perform? Yes. So someone's asking why don't you perform this test or this statistical test and so on? Yes, you can perform the statistical tests that you know from knowing statistical theory. Okay. Here the idea was to introduce the concepts of A/B testing and hypothesis testing without relying on that knowledge of statistical theory. Okay. If I were to say this is a binomial distribution and this is how you compute the p-value, then people who don't know what binomial distributions are, or the chi-square test or the Fisher test, they will not follow along, and they'll not learn what the p-value was. They will just see the p-value as the output of a function. I want them to know that the p-value is the probability of getting values as extreme as the observed one, based upon the model of the null hypothesis that we were able to construct just with the concept of an histogram and by counting things and by resampling things. So I hope everyone was able to follow that explanation and better understand those concepts. Because if I were to just use statistical theory to say, oh, this is this statistical distribution, this is how you do it, this is the function, and here's the p-value, you'd not see the graphical representation of the p-value, and it would not be clear that it represents an area of the probability of the null model like that. Okay. You're welcome. Thank you all. Thank you all for attending. It was very nice. Yeah, it can be difficult to explain these concepts from scratch, but I hope you got more enlightened about these concepts, and now you understand them better. Great. Thank you all. So there are no more questions, so I'm going to pass it to my teammates in case they want to say some closing words. And as I said, you'll be getting this notebook by email after the workshop. If not today, tomorrow, you'll get the notebook. Okay.
Carlos, thank you so much. Today's workshop was so insightful. By the active engagement within the chat, it was clear that today's workshop absolutely resonated with our participants. So if you are now motivated to further or begin your career training in data science with the New York City Data Science Academy, you are in luck. We do still have available seats for our upcoming July 6th cohorts. And additionally, we are extending a 10% tuition discounts to all students who complete their enrollment before the June 26th deadline. That is this Friday. So we encourage anyone who is interested in applying to submit an application. You can do so online. Feel free to visit our website at nycdatascience.com or simply email our admissions team at admissions@nycdatascience.com. That link is also included in the chat. So thank you all again for connecting and joining today's workshop. We look forward to seeing you again. Take care.
Thank you, everyone.